Dear students, in this class let us discuss about an important result, that is integration by parts. We already know that the integration by parts is always used to find out the integration of product of two integrable functions, and that result is so familiar. But here we try to prove this result by using the property of Riemann integrability, that is by using the fundamental theorem of calculus. Here the results say that f and g are any two integrable function on closed interval AB. Capital F and capital G are their antiderivatives, means capital F dash is small f, capital G dash is small g. Then integral A to B, capital F of x, small g of x dx is nothing but f of b, g of b minus f of a, g of a minus integral A to b, f of x, capital G of x dx. So how to prove this one? Let h of x equals f of x into g of x. What is f? Antiderivative of small f. What is g? Antiderivative of small g. Since f dash and g dash are existing means they are differentiable functions. So their continuity, they are continuous functions. Thus the product of two continuous functions is also continuous. Hence h is a continuous function. So by the continuity that by the continuity of h we can apply the first fundamental theorem of calculus. That's integral A to b h dash x dx is nothing but f of b, is it h of b into h of a or h of b minus h of a. Not h of b into h of a, h of b minus h of a. Why? Fundamental theorem of calculus states that if capital F dash equals small f, then integral A to b f of x dx is nothing but f of b minus f of a. So in the light of that argument, integral A to b h dash x dx is hb minus h. What is hb? F of b, g of b. What is h of a? F of b, g of a. 1 plus 1. Again, but h of x is f of x, g of x. What is h dash x? By using product rule. That is nothing but f of x into capital G dash is small g and capital F dash is small f. So it is f of x, g of x plus small f of x into capital G of x. Moreover, therefore integral A to b h dash x dx is integral A to b f of x, g of x dx plus integral A to b small f of x, capital G of x dx. Combines this 1 and 2. What do you get? So this can be from 1, the left side is f of b into g of b minus f of a into g of a equals, come to the right side. Right side is nothing but this one, integral A to b capital F small g capital F of x into small g of x dx plus integral A to b small f of x into capital G of x dx. So finished. That's our proof. Why? Because thus integral A to b capital F of x, g of x dx is nothing but f of b, g of b minus f of a, g of a minus integral A to b f of x into g of x dx. That is nothing but the integration by parts. Clear? Okay. Now let us consider another important result, which is known as first substitution theorem. First substitution theorem. First substitution theorem. The theorem is so important. Then come to our statement. Let your phi has continuous derivative on a closed interval j. Let j equals closed interval alpha beta. J equals closed interval alpha beta. A function phi of x. Phi has continuous derivative on this j. Means phi dash, phi 2 dash, phi 3 dash, etc. are as derivable on j, etc. are exist on j. F is continuous on I. F is continuous on I. I is closed interval A. Then which is containing f of j. f is continuous on I containing f of j. Then integral alpha beta, thus first substitution theorem states that. Then integral from alpha to beta, integral alpha beta f of phi of t into phi dash t dt, f of phi of t into phi dash t dt equals integral phi of alpha to phi of beta, integral from phi alpha to phi beta f of t dt. So this is the first substitution theorem. Statement is important. Let j equals closed interval alpha beta. Phi of x has a continuous derivative on this j. F is continuous on I means closed interval ab which containing f of j. Then integral alpha to beta f of phi of t phi dash t dt is nothing but integral phi alpha to phi beta f of t dt. So how to prove this one? The proof is so interesting. Come to the proof. Let f of x, capital F of x, equals integral phi alpha to x f of t dt. Now get the solution one. You can define a function capital F of x, that is nothing but its integral phi alpha to x f of t dt. So that means by first fundamental theorem, surely this f dash x equals small f of x. Okay? By first fundamental theorem, it is f of capital F dash equals small f. Now, let h of x, define h of x. H of x equals capital F of phi of x. Capital F of phi of x. So we define f of x is in terms of integration, and capital H of x is f of phi of x. So from here, what is h dash x? Taking derivative, so it is f dash of phi of x into phi dash of x. H dash x equals f dash of phi of x into phi dash x. But what is f dash? F dash equals small f. That is small f of phi of x into phi dash x. Okay. Thus h dash x equals small f of phi of x into phi dash x. That means, but capital F of x is integral phi alpha to x f of t dt. Here h dash x is f of phi of x into phi dash of x. So from here, what about integral alpha to beta f of phi of x into phi dash x dx. Integral alpha to beta f of phi of x into phi dash x dx equals, what do you get? It is integral alpha to beta h dash t dt. Agreed. Integral alpha to beta f of phi of t. Okay. F of phi of t into phi dash t dt equals integral alpha to beta h dash t dt. But what is h? H is in terms of this one. Since by the continuity, h is a continuous function. Hence, by fundamental theorem of calculus, it is nothing but h of beta minus h of alpha, or h beta minus h alpha. Okay, h beta minus h alpha. What is h beta? It is h beta means that equals that implies left side equals h beta. What is h? F of phi of x. So h beta means f of phi of beta minus f of phi of alpha. F of phi of beta minus f of phi of alpha. So what is that equals? What is f of x? It is integral of phi alpha to x f of t dt. So what is f of phi beta? Integral phi alpha instead of x. Here it is phi beta. So it is integral phi alpha to phi beta of f of phi beta, f of x, f of t, integral phi alpha to x f of t dt. So f of phi beta means integral phi alpha to phi beta f of t dt. Okay, minus f of phi alpha. What is f of phi alpha? That is from phi alpha to phi alpha f of t dt. What is integral a to a f of x dx? Integral a to a f of x dx is equals to 0. So what remains? Equals integral phi alpha to phi beta f of t dt. That is what we require. Integral phi alpha to phi beta f of t dt is nothing but integral alpha to beta f of phi of t phi dash t dt. That is what we require here. So this is the first substitution theorem. Agreed? Okay. Now let us consider the second substitution theorem. Second substitution theorem. How to define or how to state the second substitution theorem? The statement is, if phi has a continuous derivative, if phi has a continuous derivative on j means closed interval alpha beta, and phi dash t differs from 0. Phi dash t strictly differs from 0 for all t. F is a continuous function on an interval containing f of j. Capital F is a continuous function. Capital F is a continuous function on an interval containing f of j. Let psi equals phi dash. Let psi equals phi dash. Sorry, not a phi dash. Psi equals phi inverse. Inverse of phi function. Phi has a continuous derivative. Phi is continuous, and whose derivative exists. So phi inverse is also exists there. Thus, let psi equals phi inverse. Then integral a to b. Then the second substitution theorem states that integral a to b f of phi of t dt, f of phi of t dt equals integral phi alpha to phi beta, integral of phi alpha to phi beta f of x into phi dash x dx. F of x into phi dash x dx. Come to the proof. Phi has a continuous derivative on j. What is j? Closed interval alpha beta with the phi dash t differs from 0 for all t. And f is a continuous function. F is a continuous function on an interval containing f of j. Let psi is phi inverse, then integral a to b f of phi of t dt is nothing but integral phi alpha to phi beta f of x phi dash x dx. So its proof. Come to the proof. Proof is, yes, choose a function that g equals, define a function that g or g dash equals f composition phi, or phi composition. G dash equals f composition phi. Listen, we define a new function that is g dash, so what is g? Integral of this one. So g be the antiderivative of composition of two continuous functions f and phi. Why? Phi is a continuous function. F is also continuous on a particular interval that containing this f of j. So clearly f is phi and f are continuous on same domain. So consider the composition, f composition phi. What is g? G is nothing but the antiderivative of this f composition f. Means g is integral a to b or integral alpha to beta f composition phi of x dx. Clearly, G dash is F composition phi. So, therefore, integral alpha to beta, this means integral alpha to beta f of phi of t dt. Integral alpha to beta f of phi of t dt equals integral alpha to beta g dash t dt. Okay. But what is f? F is continuous. What is g? Continuity of g is preserved. So what about the composition? Surely they are continuous. So what is g? G is continuous. Hence, by first fundamental theorem, integral alpha to beta g dash t dt is nothing but, since g is a continuous function, it is nothing but g of beta minus g of alpha. Why? Because of first fundamental theorem or fundamental theorem of calculus in its first form. Clear? Yes. So it is integral alpha to beta f of phi of t dt is g of b minus g of beta minus g of alpha. Now consider G composition phi dash of x. G composition psi, not phi. G composition psi dash. What is psi? Psi is phi inverse. G composition psi all dash of x. What is G composition psi all dash of x? It is G of psi of x all dash. G of psi of x dash. Agreed? So means its derivative, that is which is nothing but, yes, it is G dash of psi of x into G dash of psi of x into psi dash x. G dash of psi of x into psi dash x. What is G dash? But G dash is f of f composition phi. So that is nothing but equals f composition phi of psi of x into psi dash x. Okay. Why? Because G dash is nothing but f composition phi. So it is f composition phi of psi of x, f composition phi of psi of x into psi dash x. So f composition phi of psi of x means it is f of phi of psi of x, agreed, by the composition into psi dash x. Clear? What is psi? Psi is phi inverse. So what is phi of psi? That's an identity function. Clear? Phi of psi is an identity function. Why? Because by the choice of psi, psi is nothing but phi inverse. So your phi of psi of x is an identity function. So it is clearly, it is f of psi of phi means identity, because phi of phi equals, or as phi inverse equals psi, f of x into psi dash of x. That means G composition psi dash of x equals f of x into psi dash of x. Therefore, now come to the integration. Therefore, yes, integral phi alpha to phi beta, this is our requirement. Integral phi alpha phi beta of G composition psi dash of x equals integral phi alpha to phi beta, this one, f of x into psi dash of x dx. Okay, f of x into psi dash x dx. Clear? Okay. So that means, so integral phi phi beta G composition psi dash of x is nothing but integral phi beta of f of x into psi dash of x. So that is, left side is equal, or that means integral phi beta, that's our requirement, f of x into psi dash x dx equals psi dash of x dx equals, what do you get? Integral phi beta G composition psi dash of x dx. That is Since G is continuous, psi is phi inverse, it is also continuous. So what I get? It is G composition psi of phi of alpha minus G composition psi of beta by first fundamental theorem. That equals G of psi of phi of alpha minus G of psi of beta. Okay, so that equals which is nothing but it is psi and phi. It is G alpha minus G beta because psi equals phi inverse. So psi of phi alpha is alpha itself, identity function. Psi of phi beta is beta itself. G alpha minus G beta. But what is G alpha minus G beta? G alpha minus G beta is nothing but integral alpha to beta. That is nothing but integral G alpha G beta minus G alpha minus G beta minus G alpha. Sorry, not G. Sorry. It is G beta minus G alpha. So it is G beta minus G alpha. G of beta minus G of alpha. But what is G of beta minus G of alpha? That is equals integral A to B f. What is G? Yes. So it is integral A to B or integral alpha to beta f of phi of t dt. Integral alpha to beta f of phi of t dt. That is what we will use. Okay. So this is the second substitution theorem. So these two theorems are very important. That is first substitution theorem and the second substitution theorem. Okay. Thank you.